Yeah, okay, then I'll start.
Can you, oh, maybe it's our problem. Sorry, that's us. Sorry, let me fix, go ahead. We'll change the Zoom locally.
Yeah, go ahead, don't worry.
Okay, yeah. Yeah, thanks a lot. I'll start to talk about some new developments that we had in the Atlas and Inner Detector alignment in preparation for the run 3. Let's see if we can get better with respect to what we have in the run 2. Just to, maybe it's not needed, but really a quick reminder on what Atlas is a general purpose experiment on LHC, getting what comes out from the proton-proton collision at 13 TeV in the center of mass. And now we move in the run 2 to 13.6. So really trying to ramp up for it. And what I'm most interested into is in the inner detector. That is the closest detector to the collision, to the beamline, and it's a tracker. So it's composed by 3 different sub-detectors that use different technologies. There are the pixel and the insertable B layer, the IBL, that use pixels. Then silicon strips modules, that is the SCT, the second, and eventually the transitional decision tracker that is made of straw tubes. And if you sum up all the degrees of freedom for all of them, compress, bars, layers, and end caps, you end up to almost 750,000 degrees of freedom. So quite a complex geometry to describe, and this is what the alignment tries to do it. And what we do, the alignment procedure is based on the minimization of the track to hit residuals. So we measure hits in the detector. We reconstruct the track with the tracking algorithm in Atlas, and we move the geometry in the local coordinates in order to minimize the track to hit residuals. And we have to cope with different movements of the detector. The global mechanical assembly usually move within the LHC field even. So we have to repeatedly align during the LHC field, but also we go down to the module level, but their movements are more stable, and we update it just a few times per year. If you want more details, that we released now 2 years ago the paper about the run 2 alignment, and we can see that, of course, with the dynamic alignment, that what we see, we have a better resolution, and also a description of the detector stable at the level even to of the micrometer for most of the detector. But minimizing the residuals is not doesn't call for perfect, let's say, description of the detector, because we have so-called weak modes. There are 2 types of the weak modes: the scale distortions, that distorts coherently all the layers, for example, in the direction of the track propagation. But also there are sagitta distortion, that I will come back to it, where we rotate all the detector, all the detector layers, for example, coherently, and we introduce biases of the track parameters, despite keeping the track to hit residuals basically to 0. So a track residual alignment is not sensitive to it, and we have to monitor the weak modes. And we do it by using, for example, the resonances decay, like Z and J psi, to especially mu ones. And what we do during the alignment procedure is to measure, given a constant, like set of constant and a geometry from the alignment, we measure the bias. We giving an input to the alignment procedure to constrain the tracks in order to change the geometry of the detector and to derive new constants in order to minimize the bias. And then we use these new constants to refeed the mu tracks, and in an iterative ways, in order to keep the residual to 0 and try to remove the biases from the tracks. Now going towards the run 3, after having given like an overview on the tracking of the alignment procedure that we used, there have been a lot of changes and improvement in the reconstruction suite, and in order to make it quicker, in few words, quicker and better in terms of CPU and memory saving. But I won't spend much into it, because if you are interested, there is a very interesting poster from Michaelas. So if you are interested, check it out. The only thing that I will mention explicitly is the MDN introduction. That is the mixture density network. That is a new algorithm for estimating the position of the cluster into the pixel. And this is actually very interesting because it has proven to give better resolution in a crowded detector that is expected for run 3. And therefore, we had to reprocess all the data we had during the run 2 data taking with this new suite in order also to have a common framework, a common reconstruction for all the run 2 and the coming run 3. But this brought us to another alignment iteration of the whole run 3. Well, why? Because we observed the movement of the hits of the position of the reconstructed tracks. This is because the MDN also removed the bias that was introduced by the previous version of the network that was estimating the cluster position. That you can see is also changing with the incident angle. That means a different eta of the detector. And when this is on the left is what we see in the Monte Carlo. So this bias was absorbed in the constants that we derived during the run 2 because it was based on the run 2 neural network version of the position estimation. And when we applied the constant that we derived on the newly introduced MDN, well, then we introduced a bias with the constant because we overcompensate for a bias that is no longer there. And indeed, we see a same pattern as we saw in the Monte Carlo, but on the opposite side. And therefore, we have to realign the detector, try to remove this overcompensation of the bias. So we studied the alignment procedure in order to remove it. And we had two rounds of, we separated the strategy in 2 rounds. The first round was the minimization of the track to width residual. And as you can see, for example, this is the residual in the local Y direction that is along the beam axis. And going from the gray to the red, we removed, basically, we brought the residual to 0. But as we learned from before, this doesn't mean that there are no weak modes. And indeed, we observe, for example, in weak modes that introduce the bias in the impact parameters, and therefore we use these maps of the weak parameters in order to constrain the tracks and to derive new constants and in the iteration loop in order then at the end of the alignment campaign after the second round to remove the wall bias. But the bias on the D0 was not the only bias on the impact parameters was not the only bias that we focused on, but we also observed we also tried to minimize the global Sagitta bias reduction. That means overall rotation of all the layers. So not just localized, but overall rotation of all the layers of the detector. Because the previous method that we used, that is described, for example, in the alignment paper, was not sensitive to this kind of bias, but just to local deformation, local Sagitta distortions. And therefore, we found a workaround in order to minimize it that is based, let's say, on the Z to mu spectrum of the PT of the muons. So at the first order, we expect them to be similar, and therefore, from the discrepancies of the 2 PT distribution, we can estimate with a very easy analytical formula the level of the global bias, and then inject it into the alignment iteration in order to correct the geometry to absorb it. And this demonstrates to work fairly well, and we decrease the level of the global Sagitta bias from 0.06 to 0.01 level. It is a very good achievement. We also check that we don't cancel any physics, because when we try to make 2 different PT spectrum the same, well, maybe we can cancel any asymmetry that is physics motivated in Z to mu. And we checked it in the forward background asymmetry. And as you can see, we still have the trend. So there is still the AFB there, but we just remove the wiggle or reduce the wiggle. That is the sign of a reduction of the global Sagitta bias onto the distribution, onto the data events. So just now going to the performance that we have with the new reconstruction suite in the reprocessed run 2 dataset with all the reconstruction preparing for the run 3. We see a very good description of the impact parameter at the level of micrometer or sub-micrometer, even in the transverse direction. and also stable physics performance, as you can see in the stability of the reconstructed dimuon system mass over the years. If you see from these plots, there is a missing plot, that is the sagitta. That is what we actually want to minimize. Well, I will focus this last part of the talk exactly to the sagitta, because we invested, because this was quite a workaround. The PT asymmetry trick worked fine, but okay, maybe we can do it in an optimal way. And indeed, we started to investigate why the mass method that we used this so-called mass method that we used so far was not sensitive to the global bias. This is because it was based on the movements of the dimuon mass with respect to a reference mass scanning over the detector, so overall the detector. And if we parameterize this way the effect of a sagitta bias onto the PT, we can also parameterize the movements or the differences between the reconstructed mass and the reference mass. And you can see that in case of a global bias, so the same bias over the detector, and an average truth PT of the positive and the negative muons to be the same, in average, basically, we have that the beam by beam, the reconstructed dimuon mass is basically the same as the reference mass. So the mean doesn't move. This means that the method that we use so far that is based on these differences is not sensitive to global bias, but the variance of the reconstructed muon mass would instead increase. And indeed, this brought us to implement this new method that is called var-min method, that stands for the minimization of the variance of the distribution. We can indeed write the formula before in a different way, like in a bit more fancy way, where this vector is basically a vector, where this vectorial product is a vector is scanning as an index. The bin index of the map over the scan. So basically of the eta phi map over the detector. So basically we scan in a vector overall the detector. We can compute the variance of the reconstructed mass, and when we derive and when we can minimize this function, so this formula as a function of the delta of the sagitta in a given eta phi bin, so in a given index of the vector. And therefore, we end up with a linear system, that we can resolve in terms of that we can resolve in terms of the delta sagitta, so of the sagitta bias over the map. Fine. So we have all the formulation. It's just a matter to implement it and minimize this, and so resolve, let's say, this system of linear equation. And so what we get when we compare with the mass method before, this is the map over all the detector over eta and phi of the measured sagitta bias, and you can see that the methods close, and they have also an high correlation. And this means first that, okay, the method is quite accurate, because we can reproduce something that we actually understand, like the mass method. But also it has a spoiler inside. That means that the global sagitta bias that we measure in the data, it's actually very small. And this we can appreciate in the next slide, this plot on the right and on the left, where we can see that the sagitta bias over all the time over the run 2 is actually very small, is at the level of 0.01, 0.02 TeV in average over the whole year. But nevertheless, the introduction of the var-min method is a very good improvement, because this will let us to kind of an automatic minimization of the var-min of the global sagitta bias, because if we use this method to measure the sagitta bias during the alignment, we can kind of automatically reconstruct move the geometry in order to minimize the global sagitta bias in the Z to mu events. But also it's a very nice improvement because it's much quicker. If we compare the convergence plot on the right, it takes 6 iterations for it mass to for the mass method, so from the previous method to converge, while for the var-min is really just a matter of 3 iterations. So it's much quicker, and we have to wait less in order to have decent alignment constants out. So this will give us a better global sagitta that it will be very good for precision measurement for run 3, for the next run 3, and also in a shorter time that is always better for time pressures like when you have a lot of data. So yeah, basically I'm in the conclusion, just to take away message is that Atlas is trying to get ready for the run 3, and there have been a lot of developments and a lot of novelties that were introduced in the reconstruction algorithm for the run 3. One of those is the new pixel cluster position network that removes some bias that was present in the previous version of the algorithm. We realigned and we also introduced new techniques and new alignment strategy in order to remove and to minimize the track parameter bias, keeping the residuals, track to hit residuals to a minimum. And we also introduced new methods such as the varmin that will be of a great improvement for the next round of alignment, because will let us to reduce the bias right away in during the data taking, basically during as soon as we collect the data. And that's all. Thanks a lot for the attention.
Thank you. Do we have questions on Zoom? Anyone from the room? I have. I guess it's not really a question, but I'm asking for an explanation because I'm not familiar with alignment. So, for example, on slide 10 or on slide 13, yeah, for example, here, the errors with which you determine any of these points seems to be bigger than the fluctuations. Is this because somehow you keep memory of where you were when you calculate the next alignment?
I don't know. Yeah, this the errors here are not really the error on the mean. Is just to give in the pub note is explained. This stands for the standard deviation of the distribution. Is just to give the idea of how much the impact parameter bias spread over all the map that we reconstruct. So it's quite stable. That is also a good idea, a good indication that we have more or less always the same pattern over the run 2.
Any other question? Yes.
This is Joe. So you mentioned at the beginning of your talk that you did this alignment with Z bosons and with J-psi decays, but then you primarily showed results from Z's. So I was wondering how, if your results are much worse with J-psis, or if you get comparable performance, or if if having the quite high PT tracks really makes a big difference in the alignment.
So yeah, that's a good question. So just to be clear, basically we have two rounds. Let's say the real alignment. So when we minimize the bias, the residuals is based on any track that we reconstruct, because we want to have enough statistics in all the detector, and we actually don't really mind about the physics process that is behind. The resonances we use to measure then the biases, because we need some reference for PT, for the track parameters. And we know, for example, in Z to mu that the muons come from the same place, or for any resonance that they come from the same primary vertex. So we can actually measure how much distortion can split them or can move them away apart each other. So the Z to mu and the resonances, we use just them to measure the track parameter bias and then inject them back into the ID tracks in order to adjust the geometry to reduce those. But it's a good question about the PT dependence. This is something that we also try to check. Having muons or like any tracks that are high in PT, kind of it's what we want for the alignment, right? So we want straight tracks because we want to check that things are really aligned, and we don't really want to mess up with low PT, with the I don't know, for example, multiple scattering that can happen and can a bit look at the, inference in it. These are also taken into account into the alignment in the T-square minimization. If you want the details, there are in the paper. But also we check the PT dependence, and so far we haven't seen much of the dependence of the detector. The Z2 mu is just easier because the tracks are straight, the muons are clean, and yeah, it's easy to reconstruct. So, but we keep in mind that for lower PT the situation might be different, and that's why we try also to check in JPSI.
Okay, thanks.
Anyone else? Doesn't look like it. Paolo, thanks again.